question 11. We want to find w cubed and w to the power of a quarter, where w is equal to -8 plus 8 root 3i. And it tells us to do it by writing w in polar form and then using the Moivre theorem to find the solutions. And we need to give any final solutions in exact and fully simplified Cartesian forms. So our first step is to write w in polar form. So to do this, we want to find what r is and what theta is. Oops. Now r is the square root of 8 squared plus 8 root 3 squared, which is 16. And theta, if we think about what theta is representing here, we have our point. Let's draw some axes. Our point here, which is 8 root 3i, and we want this angle around here. But that angle will be quite hard to find in itself. So what we're going to do is we're going to find this angle here. Let's call it alpha, and theta is going to be equal to pi minus alpha. So alpha here is the arctan of 8 root 3 divided by 8, so root 3. So theta equals pi minus the arctan root 3. So theta is 2 pi by 3. So now we can write w in polar form, which is 16 e to the 2 pi I by 3. So we've done that bit. Let's take that off. Now we've got to use the Moivre theorem to find w cubed. So we want to find w cubed. So to do this, we will take our w, which is 16 e to the 2 pi by 3, and the Moivre theorem says that w cubed is equal to 16 cubed e to the 2 pi I over 3 cubed, which is 2 pi I. So we can write this out as 4096 e to the 2 pi I, and we want to give any solutions in exact and fully simplified Cartesian form. So we need to work out what e to the 2 pi I is. E to the 2 pi I is equal to cos of 2 pi plus I sine 2 pi, which cos of 2 pi is 1, sine of 2 pi is 0, so that means that w cubed is simply 4096 times 1. So moving now on to w to the power of 4, power of a quarter. Then we'll do the same thing as we've just done. Let's write it there. W to a quarter is equal to 16 to the power of a quarter e to the 2 pi I by 3 to the power of a quarter. So let's say pi I by 6. Just to cancel that down. 16 to the power of a quarter is 2. So we are now left with 2 e to the pi I by 6. When we find the root of a complex number, so here we're looking for the fourth root, we know that there are 4 different roots. So if we have a quick look at w, which was 16 e to the 2 pi I by 3, then we would have 16 lots of cos of 2 pi by 3 plus I sine 2 pi by 3. Now this is equivalent to 16 lots of the cos 2 pi by 3 plus 2 pi plus I sine 2 pi by 3 plus 2 pi, and we could substitute this 2 pi by 2n pi. So we can say with surety that W is also equal to 16 lots of 2 pi by 3 plus 2n pi I. Sorry, that's e to the power. So when we then take the fourth root, that goes to 16 goes to 2e to the 2 pi by 3, which is our pi by 6, plus pi by 2i. So to find our other roots, obviously we've got our first one written here. This is our principal root. Then to find the other ones, we simply add pi by 2 to the power of e. Sorry, 2 pi by 2i. Multiply by I. So our roots are, that should be n pi by 2. We've got our principal root. Let's do this in a different colour actually. So brown. So principal root 2e to the pi I by 6 for when n equals 0. We can then have 2e to the 4 pi I by 6 when n equals 1. We can have n equal to negative 1, which would give us 2e to the negative 2 pi I by 6, and n equals negative 2, which would give us 2e to the negative 5 I pi by 6. So we've been asked to give all solutions in exact and fully simplified Cartesian form. So W equals, we're going to work along and do the same thing as we've done up here, just to put it into the trigonometric form and to evaluate it. So root 3 plus I, negative 1 plus I root 3, 1 minus I root 3, and negative root 3 minus I. So we wrote W into polar form, which gave us this bit over here. Used the Moivre theorem to find W cubed and W to the power of quarter, and we made sure that they're all in fully simplified Cartesian forms, which was exact. If it hadn't said exact for root 3, we could have written it as 1.7, but because we want it exact, we'll leave it as root 3. So I hope you found this useful. Thank you for watching.